Hey everyone again, and welcome to this video tutorial on the Linux system calls. This will actually answer quite a few of your questions on how system calls can be used in the assignment and beyond. So let me start by just reminding you of what system calls are. These are basically a set of interfaces by which the process can go from user space to interacting with the kernel or kernel functionality. And it is used for controlling the hardware, for example, creating new processes and communication between different processes that exist. Maybe on not, I mean, they might not be even sharing the same parent or anything, but they might just need some communication and some other services from the operating system, for example, reading from disk, writing from disk, getting more memory, releasing some memory, and these things. So, uh, syscalls are an abstraction, and they basically provide this abstraction to the user and the applications. The applications do not really care what kind of hard disk you're running on or what is the type of memory module that you're using. I mean, what make is it? Doesn't really care about what mouse you're looking at or what screen you're using or what even, I mean, even to some extent, what graphics card for a normal graphics application you're using, for example. So they provide an abstraction for applications on the types of on the hardware that is being used. They should also ensure system security and stability, so you should not do things that would introduce any sort of insecurity or some instabilities, some undefined behavior in the system. So they provide also security and stability. It allows the kernel to arbitrate between different processes because it using system calls you can actually check if these if two processes are competing for the same resource, which one has, for example, the right permissions, which users have higher priority, and so on. So you can actually use them to do these kinds of arbitration. And together with exceptions and traps, upcalls, they are the only legal way to go from user space to the kernel space. So you cannot, as a user level application, go into the kernel except through using syscalls. And syscalls are actually architecture dependent. Well, they are not architecture dependent. It's wrong to say that, but some syscalls are supported on some architectures, but are not supported on others. And by architectures, we are talking about the CPU architecture, for example, and maybe even some of the media types. I mean, if you have a GPU on your graphics card and these things, you can have syscalls that are only supported by your by an architecture. So if we talk about the x86, your computer processor, versus the ARM64, which is the processor on Raspberry Pi, there is a difference between the different system calls. And for Linux, there are about 335 syscalls for the x86 architecture, which is basically a normal computer architecture. And basically, that's for x86 only. So you might have a subset of that or a superset of that for other architectures. And there's a very interesting thing that not all operating systems that exist actually publish their exact syscalls. They have some abstractions over the system calls, making them even much worse in performance. The system calls are in general, I mean, since you need to do the context switching from the user to the kernel space, they are typically slower to invoke than a normal method. Although things that are implemented as kernel in kernel space might be faster because, well, they have higher priority, they do not need to ask for permissions and so on and so forth. But the context switch itself, I mean, if you have a method that can be implemented in user space and the same method can be implemented in kernel space, and when you implementing it in user space, you do not need to have any further syscalls than the one in calling user space method or calling user space function might actually make more sense because it's faster. And as I said, not all operating systems publish their exact system calls, and some operating systems are estimated to have over 1,000. Actually, Windows 8, and this is published, has 1078 system calls according to their online guide. So, I mean, Windows had that habit of actually not revealing what system calls they have, and people would actually try to hack Windows to understand what system calls are there because they might be useful for many programmers. Okay, so uh, as an average programmer, you do not typically use system calls. You do not go and call a system call directly into the kernel, but you use an application programming interface to call a system call. And that's what most people are familiar with. It might be that the API, the call for the API, actually overlaps with the name of the system call, but for example, fork. But that doesn't mean that you're just calling the system call right away. You call an API basically, and if you look at this figure, this sums up how system calls are actually how it works actually in real in programming. You typically have a print f sys.out.println in Java. I mean some print function, so printf in C, print in Python, sys.out.println or sys.out.print in Java, and you call and you call basically the function in the library, in the language library from the application. The language library calls a function that is like, for example, printf in the C library calls a write function in the C library. And this is basically the POSIX abstraction that we're going to talk about in a little while. And then this one is the one that calls the write system call in reality. And you can see that, well, you're changing from the application level I mean, and it depends on what kind of application you're running, um, uh, what kind of programming language you're actually using to implement the application. Because, for example, in Java, you even have the JVM lying somewhere in between, and so on. But in general, you basically have these transitions between the application till the language internally inside the language library and then the system call.